Here are a couple examples of changing the position of the leaving group, or you could think of them as short synthesis problems where we string 2 or 3 or maybe 4 reactions together in order to change our molecule into something larger or with different functional groups or with functional groups in different positions. When we're faced with a problem like this, I like to work backwards. So most of the time I'm going to ask myself, what do I need to do to make this last molecule? And we can observe that there is an OH here and a chlorine. So the only step, or the only reaction that we know of that can add an OH and a chlorine is the hydrohalogenation reaction, where we mix some dihalide, in this case chlorine, and water. And we're going to end up with OH added to the more substituted carbon, and indeed we see that it is on the more substituted carbon. It has created a stereocenter, and we've indicated that we form the other enantiomer as well. And that's of course because one of our intermediates is flat, it's symmetrical, and we have the opportunity to essentially form an intermediate on either side of that. And so what do we need to react with chlorine and water? Well, we need an alkene. And specifically, we need an alkene that essentially is formed between, or was formed between the OH and the Cl. So we need this alkene, 1-pentene. And then I'm going to continue to work backwards and determine what I need to put in and react to get 1-pentene. Can I make 1-pentene from my starting material? And if you look at these closely, you might say, yeah, actually we can. We can just perform a simple E2 elimination, and if we choose the appropriate base, we can remove the desired hydrogen. There are 2 different beta hydrogens, of course. We want to remove this one to form 1-pentene, and so I need a large, bulky base, and the simplest one to draw is simply T-butoxide. You can make these methyls a little bigger if you want to, but that's not essential. And so really, I can get rid of this arrow right here and this line. All we need to do is do the first E2 reaction, and then we need to do addition to alkenes. So this is a 2-step synthesis problem that takes this leaving group, turns it into an alkene, allows us to add essentially a different leaving group in a different position, if you want to think about it. Or I like to think about this particular reaction is cool because it adds 2 different functional groups instead of just one. So the hydrohalogenation is actually a pretty interesting addition to alkene reaction. Alright, so the second example here really is taking, it appears that it has the same functional group here, and again we're indicating that we have both enantiomers. So there's a stereocenter, we're going to get the other stereocenter. This is not a stereocenter, there are 2 methyl groups there, but we've added the alcohol, so we've added another OH at this carbon. And so we've learned a number of reactions that can add 2 OH groups, essentially a 1,2 diol. My favorite is probably osmium tetroxide, followed by the sodium sulfate and water. And that adds syn diol, of course. Spell that right. In this case, it doesn't matter if it's syn or anti because we can't observe that because we only form 1 stereocenter. So we don't know how this OH came to be. If we added syn or anti, we cannot make that observation. So you could choose the other, the anti-diol addition, which is MCPBA, then opened by acid in the second step. But I'm going to keep us with osmium tetroxide here. And I know that I need an alkene to react with osmium tetroxide. So this is the alkene that I need to react with osmium tetroxide to make my product. And of course there's 2 sides to this alkene. We would react equally likely with both of them, and that gives us a racemic mixture of this stereocenter. So the question becomes, how do I get from the starting material to this alkene? One possible way, I think, is simply doing an E1 elimination reaction with concentrated H2SO4. We could protonate the water, let the most stable alkene form, and that's this one. Another option is to first turn this into a good leaving group, tosyl chloride and pyridine. And then we could affect an E2 reaction. So this is E2, this would be E1, and we would want a non-sterically hindered base so that we can remove this sterically less accessible hydrogen and thus form the Hofmann product, right? This is the Hofmann product. So there are two ways to get to the alkene, and then, as we discussed, you can use any sort of dihydroxylation reaction you want because we don't see that it's syn or anti because there's only one stereocenter that's formed. So there's a couple ways to do this, either 2 steps or 3 steps. Let's look at this one. This is more of just a synthesis problem. And this one's interesting because we make this one molecule that is a long chain. We started with a ring, and so at first it might look kind of weird, but there's only one reaction we know that can cut carbon-carbon bonds and also importantly end up with carbonyl groups, aldehydes or ketones, and that's the ozonolysis reaction, O3 followed by DMS. So that's probably going to be our final step here. I'm going to erase this black line so it doesn't confuse us. So that's probably our final step. And we know that because we've cut a carbon-carbon bond somewhere, we're not quite sure where yet, and we formed these 2 carbonyl compounds. So how do we need to fit this compound back together into the alkene that it was, so that when we cut it apart it looks like this. And to do that, let's number these. I'm not going to follow any IUPAC rules, I'm just getting some arbitrary numbers. And I'm going to conclude that carbon 1 and 6 used to be connected, and thus I need a 6-membered ring. And I need an alkene between carbon 1 and 6, and so let's just number it like this. Again, I'm just numbering these so I can keep track of what was where. Okay, so at carbon 5 I had a stereocenter, and at carbon 4 I had a stereocenter. So let's establish the absolute configuration of carbon 5 and carbon 4. So let's see, that's highest priority, second highest priority, methyl is third. I get an arrow that's going clockwise, the hydrogen's in the incorrect spot, so this is S. And then if I want to establish the priority or the stereochemistry at 4, let's see, I think highest priority is right here, then the other part of the chain, and then the methyl, and so that is going to be counterclockwise. But again, the hydrogen is in the wrong position, so I need R. So I need S at carbon 5. So I'm going to start by drawing, first I'm going to get rid of this 5, it's in the way, I'm going to get rid of the 4. I'm going to start by drawing a dash, because that's easy to turn into a wedge. So let's put a dash here, and let's identify the stereochemistry. 1, 2, 3, goes like this, and so that is going to be R, and I want S at carbon 5, so I need to turn this into a dash. And let's erase this line, and let's try the stereochemistry at carbon number 4. This 2 was left over from my priorities. It was not carbon number 2. Again, let's try a dash and see what we get. So the highest priority is going to be here. Next highest is carbon number 3, and then we have third highest, and so the arrow goes like that. That is also R, and I want R at carbon number 4, so this is good. So let's erase this extra stuff that we don't need. So that's R. Okay, so now I've put the methyls on in the right spot. They're in the right configuration. And if I take this alkene and cut it right here, I'm going to get my desired product. Okay, so I was able to create, if you will, or think backwards. That's not R, that's supposed to be S. I was able to determine, using detective skills, if you want to think about it that way, the identity of this alkene based on the fact that our desired product had the 2 carbonyls on it. And the only way I know how to make carbonyls right now is to cut alkenes in half. So I needed an alkene, and most likely I had a 6-carbon ring with an alkene in it, and so that's right here. And if I want to flip this, I think if I flip it around this line, we'll see that it's starting to look similar to my starting material. Alright, so now that's looking a little more close to my starting material. Really all I need to do is put a bromine there somehow, or at least get rid of that bromine. And so in order to get here, I think we can just do one E2 reaction, right? Because if I remove this hydrogen, I form the alkene right here. Is this hydrogen going to be removed in this case? Well, remember that we have some stereochemical requirements for E2 eliminations. We need a hydrogen that is 180 degrees from the bromine. So the bromine's on a wedge. We need a hydrogen on a dash. There is one at this position right here. This hydrogen is not going to participate. It is not in the right position, and we can draw that chair, if we want to establish this. Here's the bromine. Then I have a methyl that's right down here. Then I have that hydrogen, and let's just circle that in green so we can keep track of it. This is the same hydrogen. And then I have, on this carbon, two hydrogens. So of course one of them is in the right position. And let's circle that one in red. So this one is 180 degrees from the bromine. That's that one. And so he gets eliminated, and we form the alkene right here. So this is really just a two-step reaction too. And at first it looks a lot more complicated because we have a ring going to a chain. But typically that means we just cut one of the bonds in the ring, and that's going to be this bond, because that's where we can form an alkene, and we know that O3 and DMS will cleave alkenes. So you see here, again, we're working backwards. Our goal is to find the previous intermediate, and then see how that relates to the starting material. Oftentimes it's just one step away from the starting material. Sometimes we might need to do a few things to it in order to get back to the starting material, but synthesis is all about working backwards, and you saw that here. So if you want to practice this with your friends, basically take a molecule with a functional group and write 2 or 3 reactions that you can do to that molecule, and then get a final product, and then show your friend just your starting material and your final product, and let them work it out, and have them do the same thing for you. So you can provide practice questions for your friend. It's harder to work up your own practice synthesis problems because you just created it and you know the answer. But if you swap them with a buddy, I think that that can be a very good technique for studying this relatively difficult topic. This is sort of the top of the pyramid, if you will. The goal of our class is to be able to take all the different reactions we learned and the ability to make drawings to support the expected outcome. We should be able to understand why the red H is removed in this case and the green H is not. For instance, in this case, maybe a Newman projection might be useful in a different reaction. But essentially take everything we've learned and put it together. So here we're learning we're using reactions from Chapter 8, Elimination, and now we're using reactions from Chapter 9. We're putting them all together in order to take some starting material and either change it into something completely different or make it more complex or less complex with 2 or 3 or maybe 4 steps in our problems.